Welcome to Power System Protection Lecture Series. I'm Pratap Mysore. We will continue with the fault analysis. In the last lecture, we covered per unit and percent quantities. Instead of expressing voltages, currents, impedance, and all the electrical quantities and actual values in terms of volts, amps, and impedances, and watts and watts or ohmic values. We said that we will reference that to a base quantity, which we take as a nominal number, and then we take the ratio of the actual value to the nominal, this reference quantity, and then we express it as per unit. And if you multiply by 100, it becomes percent. So now you take an example here, 800 MVA, 23 kV. We selected the base MVA as 100 MVA and base kV as 23 kV. So the generator voltage, bus voltage will be 23 by 23, 1 per unit. And then the MVA will be 800 by 100, which is 8 per unit. And the base current, if you look at 100 MVA and 23 kV, it turns out to be 10 amperes. It's around that. And then if you look at the full load current, it is 20,000 amps for this generator. So the ratio is 8 per unit. Okay. And now we said that it is time invariant, it is invariant of the voltage. The 8 per unit continues if the current 800 amps is generated and it is flowing up to 230 kV and continuing. It becomes 8 per unit. So it does not get into actual amps and volts. And we avoided representation with a simple network without taking into different voltages. We are just representing in per unit impedance and per unit quantities. So it just gets rid of these various voltage levels. Now, three-phase symmetrical components, we said that in 1918, Dr. Fortescue came back and said that you can represent these three-phase vectors, voltage and currents, as three sets of balanced vectors. And then what does it do? It allows us to represent this as a single phase system. And then we can use our known mathematical formula entities or theorems to solve and to get voltages and currents at various points. That is what our intent is. Now, if I look at a three-phase system, we can represent it with three sets of equal vectors without any angular relationship difference between the two. We call them zero sequence, VA0, VB0, VC0. They are all equal in magnitude, and then there is no time space difference. And then you have generated another set of voltages, which is same as a generated voltage. It has the same sequence of rotation A, B, and C in the counterclockwise direction. And then we represent as a three equally spaced vector VA1, VB1, and VC1. VA1, VB1 is A square VA1, and VC1 is ABA1. A is the operator we introduced in the last lecture, which rotates a vector in counterclockwise direction by 120 degrees. And now so I have a second set of vectors, which is ACB in counterclockwise direction or ABC in clockwise direction. So it has, if I take ABC as a reference, it has an opposite rotation when compared to the positive sequence, and we call this a negative sequence. So mathematically, three phases are represented as VA2, VB2, which is AVA1, and VC2 is A square VA1. Again, A is an operator which rotates a vector in counterclockwise direction by 120 degrees. So now we looked at it. So positive sequence is three vectors, has the same phase rotation as the generated voltage and ABC, and then going in counterclockwise. Negative sequence has an opposite rotation with the same phases, but if I look ACB, then it has got a counterclockwise direction, same as the positive sequence. So it is ACB in counterclockwise or ABC in clockwise rotation. So you have to be careful about it, what you're using. And zero sequence is three vectors not separated in time. So now then also we said that we know the sequence components. Some of the sequence components will give rise to the particular phase component. For example, VA is sum of positive, negative, and zero sequence voltages on the A phase. And then VB is sum of a positive, negative, and zero sequence voltage in B phase, which can be expressed in terms of A phase as A square VA1 plus AVA2 plus VA0, and then VC is AVA1 plus A square VA2 plus VA0. Okay. And now we also went through this in the last class that we can determine the sequence components, or we can extract the sequence components from the phase quantities by just some mathematical manipulations. So zero sequence voltage is just 1/3 of sum of all the voltages, and then positive sequence is the sum of VA plus AVB plus A square VC. We have to rotate them in 120 or 240 degrees on the other B and C phase to get the sum of three to equal to 3 times VA1. And similarly, VA2 we can calculate. These are all mathematical relationships. Please go through them slowly so you can understand. And then we can represent them in mathematically like this. VA0 is sum of 3 voltages and 1/3 of that. And then with manipulation of the 3 equations, we calculate the A1 and A2. And graphical method also we covered in the last class. We can plot graphically and find out the magnitude of the A phase voltage by graphical methods, which is archaic now and historic. Nobody uses this. We can easily do that mathematically. Matrix representation also we covered. Here is a matrix representation to get the sequence components from the phase components, and there can be you can represent similarly a matrix equation to get the phase quantities from the sequence quantities. Okay. Now let's look at another concept here. If the generator we know generates only the positive sequence voltage, right? So now if I look at it, if I want to get a voltage at the point of the terminal, then if there is a current flowing through the impedance of up to from the generator up to the voltage up to the bus where we are trying to calculate the voltage, it is generated voltage minus the voltage drop across the impedance due to the positive sequence current. So VA1 is EA1 minus IA1 times Z1. But when you look at the negative and zero sequence, we are not generating negative sequence voltages or negative sequence current because the generator is rotating in only in counterclockwise direction, and then it is balanced three-phase voltage just like a positive sequence. So it does not have negative sequence. So the generated voltage is 0 for negative and zero sequence. So we have to consider, because you have got sequence currents flowing through these impedances, I get a voltage drop as minus IA2 Z2 and minus IA0 Z0. So this concept we will use in the additional networks, and instead of a generator, we look at the equivalent reduced voltage source and then an equivalent impedance in series with that using Thevenin equivalence, and then we represent that and then use it for our calculation. We also looked at short circuits. We had three-phase faults, ABC, with and without ground association, and line-to-line faults, AB, BC, CA, and then line to ground fault, A to ground, B to ground, C to ground, and double line to ground fault, AB to ground, BC to ground, CA ground. They have these 10 types of faults, and then we will look at it, how we should represent our system and how to arrive at the sequence components for all these conditions in coming slides. So what is our problem? We have to determine the voltage and current at various points in a three-phase system when the fault occurs at a specific location, right? That is what it is our problem definition, right? And then solution is to determine the unknown quantities. What are the unknown quantities? Phase voltages and phase current at various points in the network due to a disturbance at a location. The solution process, what we use now is you replace the phase currents and voltages at the point of asymmetry where the fault occurs. We calculate the relationship between the voltages and currents, and then we know the relationship between voltage and current at the fault point. We call that a boundary condition, and then we convert them to sequence components and then use it backwards to go back at various points and then convert it back to the phase components. So now let us look at A to ground fault. the voltage collapses to zero at the fault point. When there is a short circuit from A phase to ground, voltage at that particular point goes to zero, correct? And then the fault current flows only on the A phase. Now, if we assume the fault current is very high and the load current is negligible when compared to the fault current, we can just assume that B phase and C phase currents will still be zero because it is not involved in the fault. So, and then A to ground goes to zero, VB and IB and IC will be equal to zero. This is our definition of a situation at the fault point. Similarly, for B to C fault, VB will be equal to VC because the B and C phases are shorted, but there is no current on the A phase. And A to B to C fault, we have currents on all the phases, and VA, VB, and VC, because they are adding, that will be equal to zero. VA equals VB and VC, that will be equal to VC, and IA will be equal to IB equal to IC. So that is your A to B to C to ground fault. Why I said zero here is when whether you involve ABC to ground or ABC, the effect is the same. B to C to ground fault, VB and C not only are equal, but they are connected to ground, so the voltage collapses to zero. And similarly, but still, A phase current is still equal to zero. These are the boundary conditions which we will use in developing theory of analyzing and calculating fault currents and voltages at various locations in the network system. So single line to ground fault, VA equals zero. So there is no fault current in B and C. So if you look at it, you can calculate, you see that the sequence current IA0, IA1, and IA2, because B and C phase currents are zero, will be equal to 1/3 of the fault current, IA, or in the phase A current, right? So if you look at this, and then VA equals zero, using that equation, I write down positive sequence will be equal to negative sum of negative sequence voltage drop, voltage, and then zero sequence voltage at the fault point. And then now we know that VA2 is IA2 Z2 minus IA2 Z2. And then because IA2 and IA1 are same, so I can write this as minus IA1 Z2. VA0 is minus IA0 Z0, which I can write it as minus IA1 Z0. So VA1 will be IA1 Z2 plus Z0. What is VA1? If you took an equivalent of the system from the fault point, if you look towards the system, and then you can represent the whole system with an equivalent voltage source and an equivalent impedance, a positive sequence, E minus IA1, I've represented like that. E is the equivalent voltage source from the Thevenin system looking from the fault point. Okay, so if you solve this, now I know the generated voltage divided by Z1 plus Z2 plus Z0 gives me the positive sequence current. So I measured the voltages and currents at the fault point, and then using this mathematical analysis, I calculated the zero sequence current at that particular point, right? And which is also equal to 1/3 of the fault current at that particular point. So single line to ground fault, if you look at it, A to ground, and then you can represent it mathematically like that. So now I know that IA1, IA2, IA0, we are using A, and then B and C and C phases can be represented A squared IA1 is IB1. So, but there is no need for us to use this A phase, B phase, and C phase because they are all equal in magnitude, just separated by the physical time by an angle of 120 degrees in positive and negative sequence, and with 0 degrees and zero sequence. So we just take out that subscript A. We can write that as I1, I2, and I0. Similarly, so IA will be I1 plus I2 plus I0. IB will be A squared I1 plus AI2 plus I0. IC equals AI1 plus A squared I2 plus I0. Okay, and V equals VA1, V1 plus V2 plus V0. It's a similar equation. We just took away any relationship with respect to phase. So we know the sequence components. We have no relationship with the phase here. We are just looking at it as representing with positive, negative, and zero sequence. And then if you want phase, then you have to rotate it by the using the operator A. So now I have, from the fault point, I somehow developed a positive sequence impedance with the generated voltage here from the generated voltage and represent an equivalent positive sequence network here. And then I have a negative sequence and I have a zero sequence. For an A to ground fault, what happens? All these three currents must be equal in these three sequence networks. We will come to this, how to determine the sequence networks in the next lectures. So at this time, you assume that you know how to develop the sequence impedance networks for positive, negative, and zero. So now I have three networks, and then I know that all the three currents are equal. How should they be connected? They have to be connected in series because the currents flow through each one of them. And then we also mathematically derive that the current I1 is E divided by Z1 plus Z2 plus Z0, which works out to be same. Okay. So in the fault analysis, we identify the type of the fault, determine the fault current and voltage relationship at the fault location, derive the sequence networks, determine how sequence networks work, determine sequence voltages and phase currents. Okay. And now, if you look at the voltage and unfaulted phases is very important for us. We'll take 5 more minutes than 30 minutes here to cover this particular aspect. VB is A square V1 plus AV2 plus V0. VB can be written as using mathematical relationship. You can come back and then look at it. VB will be A square E minus Z1 minus Z0 by Z0 minus Z1 by Z0 plus 2Z1 times E. So now if you look at mathematically, unfaulted phase voltages, you have A square E is a nominal voltage before the fault, but it gets shifted by a quantity based on the A phase voltage, pre-fault voltage here. So if you look at this, Z0 is typically 3 to 4 times Z1. If you use that Z0 by Z1 as 3, and then you try to calculate, the voltage in the B phase increases to 1.25 per unit than if the pre-fault voltage is assumed to be 1 per unit. So if you look at mathematically, for a voltage, for a fault in the A phase, B to C voltages come closer and they increase in the unfaulted voltages. And this increase in voltage is proportional to the Z0 by Z1 ratio. So now if Z0 by Z1 ratio is, if it is an ungrounded system, what happens here? If you go back and look at it, this comes to 1.73 times V. Okay. If you look at this, if go back and then solve this for unfaulted phases, it becomes, so if it has an unfaulted phase, if you go back and ground this, and the voltage on B and C will be nothing but phase-to-phase voltages as you look at it here. So if you have an ungrounded system, if you want to convert it into a grounded system, you have to add a zero sequence source, zero sequence impedance to the system to reduce the voltage on the other two phases at the fault point during, at the fault point. So if you want to keep it below 1.25, then your Z0 to Z1 ratio must be equal to 3. This is very important in your system. If you have an ungrounded grounded system, if you lose a transformer, it becomes ungrounded. You have to put a ground source to keep the other two voltages within this particular range. And then IEEE defines effectively grounded systems as the ratio of X0 to X1 to be less than 3 and R0 to R1 to be less than or equal to 1. It's 3 or 3.5, you should look at it. That is how it is defined. Effectively, when I take 3, the voltages on the other two phases will not increase by more than 25% if you keep this, if you keep the Z0 to Z1 ratio equal to 3. Now, if you look at phase-to-phase fault, VB equals VC, IA equals 0. So when IA equals 0, then and I0 will be equal to 0 because IB will be equal to minus IC. So IA equals 0. I0 is I1 plus IA plus IB plus IC, and IB plus IC will be equal to 0. So zero sequence never flows. So you get an equivalent system like this. E and positive and negative sequence impedances are connected opposite to each other, and then you get this relationship. You can look at network protection and automation guide, and then try to solve these uh, yourself and to get a better understanding. Similarly, phase to ground fault, the negative sequence and zero sequence networks come in parallel and get connected in series with the positive sequence, and then you can calculate the currents. Okay. In a three-phase fault, there is no negative sequence, there is no zero sequence, and it is same E, and then Z1 you put a short, and I1 is E divided by Z. So it is same as the fault current is equal to the phase current. Okay. So this is how we can represent it, and then we will go through and look at the references, and please go through and then refer to network protection and automation guide and Alstom, which I said you have to send an email and you get a free copy from Alstom. Please look at 3, 4, 5 to get an understanding of that. In the next lecture, the only unknown we had here was how to develop the sequence networks, and we will work on it and then look at how to develop the sequence networks in the next class. We'll see you then. Thanks.